Right, here's a problem to do. This is like what the kids will have to do in our class. So we need our calculators out?
Yeah.
All right, let me get
your
my
calculator ready, guys.
let me get my calculator. There it is. Let's put it in the handy.
And they need to follow along with us, right?
Yes, they better be following.
Yeah. So it's really better, guys, if you're going to follow it.
Yeah. Get your calculator out and turn it on. Don't just write down what I write. You need to do it too. So here's our problem. The specific heat of graphite is 0.71 joules per gram degree Celsius. And remember, important things I underlined so that we know that's a key term.
Right, make sure you underline that one too, guys.
All right, here's what it's asking us to do. Calculate the energy needed to raise the temperature of 75 kilograms of graphite, that's important, from 294 Kelvin to 348 Kelvin. So let's make a list of the things that we already know about this. We know we have to calculate the energy.
That's your unknown.
Right. And that we call Q. So that's what we want to find out. Where we know that C was the first thing they gave us. The specific heat is 0.71 joules per gram degree Celsius. Yep. Okay. We pretend to work, right? And then what else did they tell us?
75 kilograms of the substance, which is the mass, or M in the...
Right. And notice the equations in C
Oh.
grams. These units are grams. And we need to change kilograms to grams. Do you have a fast way to do this?
I know I can do that. It's just multiply by 1,000.
Right, just multiply it by 1,000. Another quick way is to take that decimal from here and move it over
They
3
do
times.
their King Henry.
Yeah, that can help us out when we have to convert. Oh, now I erased too much. That's okay. We'll put the zeros right there.
Like moving to the left and moving to the right.
Yeah, we taught that a long time ago, so we already know how to do that. Oh well. Now let's do temperature. We need to find
change in temperature. See, you were given 2 temperatures, right, Miss Gray?
Right, exactly.
Yeah, don't be confused about that, guys. Just follow along with me.
And we want to do final minus initial. So what is my final temperature?
It says from 294 to 348. So I bet the final is 348. Is that right, Miss Gray?
That sounds right.
Yes.
348 Kelvin. And then we're going
The initial
was the from.
Yeah, from.
That's the initial.
So I'm going to use my calculator.
All right, I'm not ready yet. I'm going to put it in the equation. So you can get your calculator going because you're ahead of me. But I'm going to put these numbers into our equation. All right, first let's write down what these things.
Yes.
Q equals
M is M C changing to.
MC delta T has a nice rhythm.
Yeah. MC delta T. That's easy to remember, Miss Gray.
Right.
Q equals MC delta T.
Right. So if you can say it with a rhythm, it will help you remember.
Yeah.
Q equals MC delta T. Some of my students call this MCAT.
Oh, yeah, it's like an A.
Right.
Yeah.
MCAT.
Which one is easy for you to remember?
Yeah. Use whatever method you like.
Yeah.
So we'll
now we're substituting the values, right?
Right. So for mass, we put in 75,000 grams. And for C, we put in the 0.71. And I'm not going to put all my units because I showed how that cancels.
Yeah.
And shall we do this math now, or do we already?
Yeah, we can do like
we'll put this.
Yeah, we have change in temperature.
Okay, so 348.
Whatever, yeah.
Minus 294. And I think that's what I will start with in my calculator.
Yes, okay.
Okay? So let me just click the thing, turn my calculator on, and it's on. So I'm going to do 348 minus 294. Because my parentheses says, do the subtraction first.
Yes.
Right?
Yeah.
And now I can do the multiplication So multiply by 75,000 times, okay, where's my pen? I clicked on something else. Sorry guys. Not sure what that was all about. And now I have a circle. Oh, is that confusing? Okay. Okay, 75,000
Times
0.71.
0.7.
Yep, it's going. All right, now hit enter, and this is our overall heat change. That looks like a really big number. And I just went away.
48.
That's okay, you got my calculation going too. So we'll write down what your numbers are. Not sure why that went away. We didn't get the same number, so let's try it again.
Okay, so it's 3.
Okay, so 348 minus. What? Oh, I have two calculators.
Oh, yeah.
How do I have two screens? All right. Let's do this. Okay. Yeah, that is. Here's my number. Are you getting the same value as I did? So I got. Oh, calculator turned on. I have a negative number. That is a negative. Yeah. Order of operations. That's why we do this. We want to make sure that we can all do it right. And obviously, I did not. So 348 minus 294 should be a positive value.
Yeah, it should be a.
Okay, so I'm going to hit enter now. Okay?
And then
I think that's why I got the wrong answer, because we didn't hit enter. Times 0.71. And I'll hit enter, and then multiply by 75,000. And that's
we have
what
the same
you
number.
Okay.
Yeah.
So we get a positive value. And it's 287,550, and that should be joules because everything else canceled away.
Yeah.
And now we'll have to look back here. I had 2 sig figs, 2 sig figs, and 3 sig figs. So our answer can only keep two significant digits. So it looks like the 7 is going to make a difference
Yeah,
here.
so
We
is
better
it
run them.
positive 29?
And then 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. This number may be easier to write in scientific notation.
Yes.
Or for us to say
2 point.
this many kilojoules. We could also, we could call it kilojoules when we had kilograms.
Yeah.
That makes sense. All right, well that's how we're going to solve these problems. And when we get to the end of a problem, I'd like my students to put a box around their answer because that's the way I like it. Am I doing that? Too quick? And change the sign? Okay.
There you go.
I think we got it. So let's look at another problem. This is our second example. Before we just
It's a very long problem, Greg.
Oh, wait, we'll go faster this time because we know what to do.
Yeah.
All right, this time in example 1, we raised the temperature. We didn't change what it is, we just changed its condition.
Yeah.
Now we're going to have a chemical change take place. We'll see how to calculate the heat change if we have a chemical reaction. So here's the important stuff. We have 50 milliliters of water that contains 0.50 moles of nitric acid, and its temperature is 22.5 degrees Celsius. Remember we used nitric acid for the copper lab.
Yes.
We had to do that part in the hood because it's very dangerous.
It's very dangerous, yeah.
We're going to mix that together with 50 milliliters of water. And in the water it has 0.5 moles of potassium hydroxide, KOH, and that temperature is also 22.5 degrees Celsius. So basically the temperature that our labs are, that's about right.
Yeah.
And we're going to mix them together in a styrofoam cup calorimeter. So basically, we pour two things into a cup and let them react. And then we're going to measure how does the temperature change. So our temperature increased as a result of this reaction to 27.3 degrees Celsius. We want to know how much heat, this time it says in kilojoules, how much heat was released by this reaction, how much heat is Q. And we're asking us a question. I'm going to circle that. That's our target.
Okay, that's the unknown, yeah.
Right? So we have a couple of things going on here. So we're trying to find out the heat of the reaction, how much heat was released by this reaction. Well, let's draw a picture. So I have nitric acid and potassium hydroxide. So in one container I have HNO3, and my other container has KOH. And we're going to combine them into one container. It says a styrofoam cup calorimeter. So we draw styrofoam cup. There we go. So I'm going to pour this in, and I'm going to pour this in. Okay, so now help me understand how much is in here now. I poured 50 milliliters of this with 50 milliliters of that. What's in this cup?
Is that 50 plus 15 is correct?
Of course. Yes, 100. Yes. 100 milliliters now of water. So here's our tricky part. What is the mass of 100 milliliters of water? Hopefully our students remember that the density of water is 1 gram for every 1 milliliter. So that will make this conversion easy. For water, you can do this. Not for anything else, but water has this density, 1 gram per milliliter. So if we have 100 milliliters of water, we have 100 grams of water. That's important.
Yes.
Okay, so this is the heat of the water, and this is the mass of the water. Now let's talk about the temperature of the water. All right, so our water temperature started out at 22.5. That's initial, so I'll put that back here. 22.5. And then it increased to 27. So that was our final. 27.3. Okay? Okay. And you also know the specific heat of water.
Oh, is that in the table?
In the table. So we better find that in the table. That's not the one I need. Get it too quick. No, oh, finally when it clicks, then I give up on it. Here we go. That's it. It was before finish.
There you go.
There it is. Here's water. 4.18.
Yeah.
That sounds familiar, right?
Yeah.
This is 4.184 is the specific heat of water. We just talked about how that's joules and calories. Calories only uses water. It compares everything else to water. All right, let's go back to our example.
Example number 2.
Yep. Okay. So C is specific heat.
Heat is 4.18.
And I'm going to use another system, 4.184. Okay. And that's in joules
Per gram degree Celsius.
Now, did you notice in our last problem we used Kelvin?
Yeah.
And in this problem we're using Celsius. Well, it doesn't really matter because if I add 273 to both of these numbers, the difference will be the same. So it was important in the gas laws that we changed all our temperatures to Kelvin.
Okay.
But in calorimetry, it's not important. As long as we have them both the same.
Okay.
All right. So now let's talk about just the water in this container, in our cup. For the water, the amount of heat was going to be then 100 grams times C, 4.184 grams degrees Celsius.
From the formula
Oh, we should write that. Q equals
M
MCAT.
MCAT, yeah.
MC, delta T.
Delta T.
Good rhythm. MC, delta T. And now let's subtract these right now. Okay, 27.3
27.3
minus 22.5.
minus 22.5, and that should give you 4.8.
Okay, 4.8 degrees. So now let's calculate the value of Q. This is for the water. So I'll get my calculator. Since you're running yours, I'll do that over here. It is. Turn it on.
So that's 100.
Okay, 100.
Minus 4.184.
That's 4.184.
Minus 4.8.
4.8. All right, did you and I get the same number?
Yes, exactly.
Oh, good. I like it when you get the same. That makes me feel better. So we have 2,008.32. And that will be joules. Now, I did emphasize that this is the heat for the water, right?
Yeah.
Okay, that's not the same as the heat for the reaction. So let's talk about this. The reaction is nitric acid and potassium hydroxide. So see that this Q is a positive number here.
Yes.
It is. The temperature of the water increased when potassium hydroxide reacted with nitric acid. And this is an acid-base reaction. So we're making water and a salt. In this case, potassium nitrate. It's running into my picture. So this is the reaction. This is the focus of our attention. We have to do a whole new calculation here. Oh, that was a lot of work. Well, it's easier than that because of the law of conservation of energy.
Oh.
We know whatever the water absorbs is equal to.
It's conserved, right?
Yeah, it's equal to the amount that the reaction released. The thing that's going to change is the sign, because one of them was absorbed, the other was released.
Released, yeah.
So we changed the sign, but the magnitude is the same.
It's the same.
So for finding the heat of the reaction, we just have to change the sign of the heat of the water.
And then it will now become minus.
Move this out of my way. And that's okay. So we will have a negative
2,000.
Oh, let's do 6 right now.
Okay. How many 6 things?
It's like 2.
2, yes.
All right. I'm going to So, all right, and in kilojoules anyway. So, 1, 2, 3.
Right?
Yep. So 2.0 kilojoules. Can you see that decimal there?
Yes.
All right, so it's negative 2.0 kilojoules for this reaction, because the reaction is our system, and it gave its heat away, so the sign is negative.
Yes.
And of course, since we're done with our problem now, I want to put a box around my answer. The screen got very crowded. I want to be sure that
What is the
find
answer?
it. Yes,
Yeah.
here is my answer. So put a box around it because that's the way I like it. Guess what? We are done.
Yay!
Yeah, that's it for podcast 1 in thermochemistry.
And we gave them 2 examples, right?
Yeah.
But they're going to do more. Are you ready to do
Of
more?
course they do more. Because that can't
We
be
need
all.
practice, right?
Of course we need practice.
Practice makes.
Practice makes perfect.
Yeah.
And there's examples in your book for you to work through.
Yes.
We'll get that in class, so you all have the support that you need, but you can do it on your own too. And come to us and show us what you've done.
Yeah.
You guys are doing great. Keep up the good work.
Yeah.
Okay, bye-bye.
Bye.